In this video, we're going to use what's called the rational root theorem to find potential zeros of a polynomial function. So on this slide, you can see the definition of the rational root theorem. And what it states is if f of x, now this right here looks like a lot of gobbledygook, but what this really represents is just a polynomial in general, because polynomials can have all different degrees with all different coefficients. So it's saying if a polynomial has integer coefficients, so you have integer numbers for all of those coefficients of x, then every rational solution of f of x equals 0. So this is saying we are trying to find the x-intercepts, has the following form. So you can see here that we have a fraction that is formed from p and q. P consists of a factor of the constant term of a sub 0, and q consists of a constant term of a sub n, which is the first leading coefficient. So what we're going to do in order to find all of the possible zeros is we're going to pair up every single factor of a sub 0 with every single factor of a sub n and find a list of possible zeros, and then we'll use that list of possible zeros to test out and find what the zeros of our function actually are. So let's complete an example of this together. So let's take a look at the factors of our a sub 0 value, which in this case is negative 12. And let's take a look at our factors of our a sub n value, which is our leading coefficient here. So I'm going to just focus on the 12 here and find all the factors of 12, and I'll show you how we'll account for those negative numbers at the very end. So we account for the factors of 12, which are 1 and 12, 2 and 6, 3 and 4. And then we have the factors of 2, which are 1 and 2. So what we're going to do here is we're going to pair up all of our p-values, which are associated with the factors of a sub 0, and we're going to pair them up with all of our q-values, which are associated with the factors of a sub n. And what we're going to do is we're going to create a list of possible factors or possible zeros for that polynomial function by pairing up all the p's over all of the q's. So let's start by pairing up all of the p's over all of the q's, and let's start with q1. So if we do 1 over 1, that simplifies to be 1. 2 over 1 simplifies to be 2. 3 over 1 simplifies to be 3. 4 over 1 simplifies to be 4. 6 over 1 simplifies to be 6. And 12 over 1 simplifies to be 12. Then if we look at q of 2, we do the same thing. So we go through all the p-values. 1 over 2, which doesn't really simplify further. It's still 1 over 2. We then have 2 over 2, which is equal to 1, but I can already see that 1's a value I already found, so we don't need to include that. I then have 3 over 2, but that one doesn't simplify further. I then have 4 over 2, which simplifies to be 2, but that's a value I already accounted for, so I can ignore it. 6 over 2 simplifies to be 3, which is a value I already found, so I can ignore it. 12 over 2 simplifies to be 6, which is also a value I already found, so I can ignore it. So our list of possible factors include the following. We have 1, 2, 3, 4, 6, 12, 1/2, and 3/2. But we also have to always accommodate for both the positive and negative versions of those, because every single number, like negative 12, can be divided by positive and negative numbers of its factors. So we're going to include plus or minus 1, plus or minus 2, 3, 4, 6, 12, 1/2, and 3/2. So what we have here are a list of all of the possible factors for this polynomial that can be made out of these integer coefficients. So what we can do is go through and test all of these values and look to find factors that work in this polynomial.